Okay, uh, in this video I'm going to address a question about how fast objects move. I'm going to follow this video with another one about how far they move. And the idea is going to be to introduce you to three equations that are going to be useful for describing motion. So this is video part one, and we're going to look at the question of how fast do things move. So let's take a look at the up and down throw. I'm going to draw a stick person here, and I want to represent the person throwing the ball straight up. And so maybe at the very beginning, in position A, the ball is in the person's hand and they are giving it a throw upwards. So this arrow represents the ball's velocity. Okay. Now, what I'm going to do is I'm just going to sketch the ball in future positions. So when it gets up a little bit, we'll call that position B. And we know that the velocity will be a little bit less. So I'll make that arrow shorter. I'm going to draw it again. C. And now that velocity vector is even smaller still. Now, at some point, the ball is going to reach its highest point. And so I'm not going to draw any velocity vector. So it's on its way up, it reaches its maximum height. Now, I drew the ball moving sideways a little bit so that we can keep our picture clear, but you can think about this as if it was just moving straight up and down. On the way down, the ball will, of course, do a mirror image type of a thing. So as it's falling, now the velocity becomes negative, and so E lines up with C. In F, it's moving faster. And in G, when it comes back to the level that it was thrown, it's moving really fast. Now, we haven't really proven that these heights are the same, that A and G are the same, that B and F are the same, etc. But we'll show that, okay, later on. Okay, so what we want to do now is answer this question, how fast? And so let's make a table. And we'll make three columns. The first column is going to be the location. And so it's going to be A, B, C, D, E, F, and G. Okay? And then we're going to look at the time. And we're going to record that in seconds. So T is the variable, S is the unit. And let's say that the ball is thrown at 0 seconds. And when it gets to position B, that's at 1 second. When it gets to C, it's 2. And so on. And so the ball spends 6 seconds going up and coming down all together. Okay, here's the last part. What does the velocity look like? And let's track that in meters per second. And at this point, I'm going to make a statement, and I'm going to say that let's pretend that this ball is thrown at 30 meters per second in the upwards direction. I'm even going to put that on my picture. So somehow the person knows that they're throwing at that speed. So the question is what happens to that 30 meters per second 1 second later? Okay? And we know that it decreases because common sense tells us that things slow down when they're on their way up. But what we also know is that the acceleration of gravity is around 10. Okay? And that means that every time a second goes by, the velocity is going to change by 10. Again, common sense tells us that the velocity should decrease by 10 if an object is traveling upwards. So at 1 second, that brings us to 20 meters per second. And what you can do is apply the same reasoning for the remaining times. So at 2 seconds, the velocity is decreased to 10 meters per second. And at 3 seconds, the ball momentarily stops moving. That's very important. Okay, I'll even circle this point. That's the ball's turning point. Okay, right here is a turning point. And yes, the object stops moving for an instant. It has to in order to change direction. After that, the ball's velocity is going to become negative. And you could just come up with the values by continuing to subtract 10. And what you'll notice is that when the ball gets into position G, its velocity is negative 30, which is the opposite of the velocity when the ball was first thrown. And so what that means is if you throw something up into the air, it will come back to you with the same speed that you threw it. Of course, all of this is in the absence of air resistance. So this is kind of an ideal case, but it's actually pretty close to the truth for small, compact objects like baseballs and things like that. All right, so what about the equation? The equation we've been using when we came up with these values is this one. It says V final equals V initial plus acceleration times time. Okay? And I want you to think about it. In this case, V final was what we were solving for. And in this case, the V initial is going to be the 30. So what we're using is V final equals 30 plus acceleration times time. And as we mentioned, the acceleration is 10, but our coordinate system is going to make us choose negative 10. And that's because we chose at the beginning implicitly to make up the positive direction. And so you have to be careful when you use this equation to make sure that you watch your pluses and minuses. Because we chose up to be positive, we have to go with a positive 30 for the initial velocity, and we have to make the acceleration of gravity negative 10. Okay? But you can try this. This formula will give you any of the values now in this table. Right? So 30 plus negative 10 times 0 is 30. 30 plus negative 10 times 1 is 20. And you can go all the way through. By the way, sometimes you might want to use not 10, but you could use 9.8. That is a more precise value, and I encourage you to use 9.8 when you solve problems in homework. But for the purposes of today, we'll just use 10. All right, so this answers the question of how fast, and we have an equation now we can use. And that allows you to find the instantaneous velocity of an object as it's in free fall. The last thing I'll end with here is just to make a connection to something that I hope you know about already. If you were to make a graph of these velocities versus time, I hope you can see that you'd be starting at a positive 30, passing through 0, and ending at a negative 30. And because you're always taking steps of negative 10, that graph should be linear. So here is your plus 30 velocity, here's your 0 velocity, and here would be your negative 30 velocity. And so that graph also is going to really support the idea that acceleration is constant. And that was the graph that we saw in our lab. Okay, thanks. That's the end of this first video.